Let's learn about the problem of representation in computer science using binary bulbs. To start with, we're going to click Game Mode on, and we're going to click the number 63. So it's going to try and ask us using the bulbs to make the number 63. If we simply start clicking up, you'll see that the light bulbs will turn on, and we could solve it this way. But let's solve it by actually just clicking the light bulbs. So we're going to start on the left-hand side, and you'll notice that there are place values for each of these light bulbs. If I turn the leftmost one on, we get the number 128 in binary. So if I want to make the number 63, we're too big. We cannot use this one. If we turn on the next one at 64, it's only going to get bigger from there. So we cannot have either of these two on. If we click 32, well, maybe we can do it. Let's check by turning all the other ones on to see if we need this 32 on. And turns out, without having this 32 on, we're not going to be able to get a number high enough to get 63. So, yes, in fact, we do need this light bulb on. And then we can do the same exact check where we can turn the other ones on to see if we can get up to that number. If we cannot, we must turn the next one on. And you'll see that 48 is just 32 plus 16. It's adding these values together. And if we continue to turn these bulbs on, and you see as it adds up, we're able to get 63 by turning these light bulbs off in the pattern of off, off, on, on. So this pattern represents the number 63. And if we were to turn the light bulbs off and shift those over to zeros and ones, it would be this string of binary digits, or 8 bits, that we can represent this with. Let's learn a little bit about the problem of representation before we do more with the binary bulbs. So in this lesson, we're going to learn how to represent letters. We're going to learn how to represent colors, images, videos, and even audio. And it all comes down to this diagram of input, black box, output. And you can argue that computer science is what happens in this black box. You have some input, like the click of a mouse, and you have some output, in other words, what happens on the screen. And input can be anything from typing to talking into the microphone that I'm doing right now, anything that is able to be input into a machine, and the output is what happens as a result. We can see that the machine code is what is taking your input and transforming it into an output. And at the end of the day, the transformation of input to output is computer science. And exactly how do we turn this electricity input into some sort of outputs? Well, that is the problem of representation. In other words, how do we transform electricity into letters and colors and images and videos and even audio? So let's get into it. To start representation, we're going to start counting in unary, which is essentially tally marks, which is known as base 1. So if we counted 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, the way that you probably counted as a child before you just used your fingers to count. That was unary notation, which is a number system with only one number in it. Un is like uno, or un in French, meaning base 1. One number is an un. Whereas a different number system, base 2, which is what we're going to be talking more about, has actually two numbers in it, which is bi, like bicycle that has two wheels. So binary has two numbers in it. And binary has what's called binary digits, as the digits that you will be using is the smallest value that we can represent information with, which is either a 0, which you can think of as like a light bulb that is off, or a 1, which you can think of as a light bulb that is on. So 0 off, 1 on, which is a bit different than the number system you're used to, known as the decimal system, which is base 10, based on the fact, we believe, that we have 10 fingers, which is what we use to count, and those 10 digits are 0 through 9 for a total of 10 digits. That's base 10 number system is called the decimal system because dec means 10, and a decade is 10 years. So in the binary number system, with only two digits, 0 and 1, we are going to be counting using just the 0 and the 1, two different digits. Binary digits called bits. And you might even notice that the power symbol is a 0 with a 1 through it. So base 10, this hieroglyphic symbol you might think of as just 1, 2, 3, but it actually stands for not 1, 2, 3, but it stands for 123. But unlike most hieroglyphics that you might know, the reason for that representing that isn't just because it's a picture image, but it represents a particular pattern that we've all agreed to accept, such as maybe this pattern could represent a dog smiling, and this pattern could represent a dog frowning. It's just an arbitrary pattern that we've all agreed to collectively. So speaking of 1, 2, 3, we actually have place values with the decimal number system, where we have the ones place, the tenths place, and the hundredths place. So in the representation of this number, we actually have 1 100, 2 tens, and 3 ones. If we then do the arithmetic, we can see that we have 100 plus 20 plus 3. So this is not just the number 1, 2, 3, but it is actually 123 by adding all of that up. And that comes down to the base values, where the actual digits, the ones place and the tens place and the hundreds place, dictate what we're adding up. And we're going to be then using that same exact process, where instead of multiplying by 10, because it's a base 10 number system from 1 to 10 to 100, it's actually a base 2 number system, where we get 1 to 2 to 4 to 8 to 16 and so on. So the thing that we multiply by is going to be different because we are in a smaller number system. There are only 2 numbers that each digit can possibly be, as opposed to 10 numbers that every digit can possibly be. So count with me now when we count with the binary decimal system, which will look a little different from the decimal number system. So this is the number 0, doesn't look any different, but this is the number 1, which still doesn't look different, but now this, although in decimal looks like 10, this is actually the number 2, because it is 0 4s plus 1 2 plus 0 1s. And we have 2 plus 0 is just the number 2. This is 3, 2 plus 1, 4, which is 4 plus 0 plus 0, 5, 4 plus 1, 6, 4 plus 2, and 7, 4 plus 2 plus 1. So that is how we count in decimal if each bit or binary digit can only have either a 0 or 1 for its value. And just like in decimal, if we need another place, we add another binary digit, and we can then represent up more information. Now we have 4 bits, and we can represent up to 8 plus 4 plus 2 plus 1 for 12, 13, 14, 15, including the 0. That's a total of 16 things that we can now represent with 4 binary digits. And typically, we don't use 4 binary digits because 16 is not that many things we can represent, but we typically use 8 binary digits, which is represented in our example with these light bulbs. So 8 bits actually is represented and called, in some pattern, a byte. A byte is 8 binary digits, or a bit, a binary digit, is just one of those digits. So we can represent a total of 256 things with a whole byte of binary digits of information. And you might be wondering, and this is where it clicks, like on your phone or on your iPad, when you run out of storage space, you have physically run out of these little switches, these binary digits. A kilobyte is when you have 1,024 bytes, which is a lot, multiply that by 8 number of bits, little switches that are inside your phone. A megabyte is approximately 10,000 bytes. A gigabyte, which is probably what your phone's storage size is approximately 100,000 bytes. So if you have 64 gigabytes of storage, you have 64 times 100,000. So you have about 6.4 million bytes in your phone. In other words, you have tiny little on and off switches that can be flipped in a pattern to be representing some piece of information. A terabyte is approximately 1 million bytes, and it goes up even from there, petabyte and higher, up to flops of information. So all of these bits are able to represent information if we give it a certain pattern, such as the capital letter A, which we've arbitrarily given the place value of 65 in decimal. So if you were to create the binary pattern of 65, if we go over to our binary bulbs and we go represent 65, that would be off on, off, 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 on, this pattern of zeros and ones, which you see here on screen, would represent the number, or this pattern, which would represent the capital letter A. And arbitrarily, why does 65 represent A? Well, many years ago, we created a system called ASCII, which is the American Standard Code for Information Interchange, which is a fancy way of saying we made a table, and that table looks like this. When you think of this table, you can kind of think of it as like a Google Translate, but for computers, where we translate a particular pattern of zeros and ones into representing letters on the screen. It uses 7 bits originally. Now we've improved it to have even more, but originally there were only 128 characters that were on the table, which posed a problem for like all of those special characters like the accents we have for other languages, which we'll get to. But it's basically computers speak in zeros and ones. ASCII is the dictionary. It looks it up. And then we can use that dictionary to assign numbers, letters, and symbols. Any computer with that same dictionary understands other computers, regardless of the brand or type, which is how an iPhone can talk to an Android or a Mac or even a Linux computer, and that text is like a secret code. So if we look on the table, we can see that the number 65 in binary is assigned the capital letter A, and we can then look up all other values, and we would be able to see what it represents. So if we had this pattern of 24 binary digits, or 3 bytes of information, we would actually get, and we can look up this pattern where this is the number 72, this is the number 73, 72 is H, 73 is I, so we would have 72, 73, which is high, and then 33 is actually the exclamation mark. So this pattern is HI exclamation mark when we look at the table. And we can see that we are able to break this pattern down and encode a particular message, which just means ASCII is translating this 24-digit binary digits, or 3 bytes of information, into HI exclamation mark. This string of zeros and ones goes from your computer over the internet to your friend's computer, and then that computer uses the dictionary after traveling there to translate it back to high. So you tape HI, hit send, it goes over, it translates that into the machine code of that string of 24 zeros and ones. Then it goes over the internet to your friend's computer. It reads the 24 binary digits. It uses the dictionary and translates it back to I in your messaging app, which is how computers are able to use machine code in the dictionary. Just like different countries can use different translators, ASCII helps computers from different places talk seamlessly. And now there are more advanced dictionaries because we are limited to the number of characters, where originally this is what the keyboard looked like, but now we have special characters like these symbols, which weren't in the original table. So we would have just gotten a bracket set, an empty, we wouldn't have gotten a symbol. It would have been missing, essentially, if you tried to send a character there. And now we even have emojis, which is literally the Japanese word for picture image. And they are just that. They are, picture images on a keyboard. Notice it's the emoji keyboard, where they have a pattern assigned to them using, instead of the dictionary called ASCII, the American Standard Code for Information Interchange, the dictionary is called Unicode, where in Unicode, we can have far more binary digits, such as a number like this, which I believe is 32 binary digits, and that is 4,036,991,106, and this binary string of 4 bytes, instead of the bytes, the 1 byte that was there, or 7 actually, it was 7 digits, not 8, it represents this pixel on Apple, and this pixel, or this emoji, on Android. So you'll notice from Apple to Android, even though the pixel image is, or the picture image, the emoji is different, the actual thing that it represents is the same. It's just the way that it's represented. And I think that's enough for this video. We've gotten long enough. I'll see you guys in the next video. Peace!